Hello, and welcome. I'm so glad you're here. Before we begin, I'd love it if you could share in the comments where you're listening from and what time it is for you right now. It's always a joy to see people tuning in from different corners of the world and at different moments in their day or night. I also want to take a gentle moment to thank those of you who have already subscribed to this channel and who keep pressing that little like button on the videos that you find most valuable. It truly helps me know what resonates with you, and it helps others find these calming spaces too. And if you ever have ideas or topics you'd like me to explore in future videos, please feel free to suggest them in the comments. Your thoughts and inspirations are always welcome here. So, with that said, let's begin. Chapter 1. Understanding Quantum Mechanics Fundamentals. Imagine a world where the rules of reality bend and twist. A realm where the very fabric of existence is woven from the threads of uncertainty and probability. Welcome to quantum mechanics, a field that challenges our traditional understanding of nature and invites us to ponder the mysteries of the universe. At its core, quantum mechanics is the study of the fundamental building blocks of matter and the forces that govern their interactions. It is a world that often defies common sense, yet holds the key to understanding the intricacies of the cosmos. The journey into quantum mechanics began in the early 20th century, a time when physicists were grappling with the limitations of classical physics. The classical theories, which had served humanity well for centuries, began to falter when faced with the behavior of the very small. In this age of discovery, figures such as Max Planck and Albert Einstein emerged, laying the groundwork for a new understanding. Planck's introduction of the concept of quantization in energy led to the realization that energy is not continuous, but rather exists in discrete packets called quanta. This radical idea shattered long-held beliefs and opened the door to a new realm of scientific inquiry. Einstein further propelled this revolution with his work on the photoelectric effect, which revealed that light behaves as both a wave and a particle. This wave-particle duality is a cornerstone of quantum theory, suggesting that entities such as light, which we often perceive as waves, also possess particle-like properties. Picture a serene lake, where ripples spread across the surface, representing the wave nature of light. Yet when you cast a stone into the water, it creates distinct splashes, embodying the particle aspect. This duality is not merely an abstract concept, it is fundamental to our understanding of the universe. As we explore the implications of quantum mechanics, it is essential to consider the entities that inhabit this realm. Electrons, photons, and other quantum particles are not merely the building blocks of matter, they are dynamic actors in the grand play of existence. An electron, for instance, is not confined to a single position or path. Instead, it exists in a state of probability, described by a wave function that expresses the likelihood of finding it in various locations. This notion of probability introduces a fundamental shift in our perception of reality. How can something be both here and not here simultaneously? This paradox invites us to embrace the complexity of the quantum world. The significance of wave-particle duality cannot be overstated, as it challenges our intuitive notions of reality. It compels us to reconsider the nature of observation itself. When we measure a quantum entity, we collapse its wave function, forcing it into a definite state. This phenomenon raises profound questions about the role of the observer in shaping reality. Are we mere witnesses to a predetermined universe? Or do our observations influence the very fabric of existence? This inquiry has captivated the minds of scientists and philosophers alike, leading to a deeper exploration of consciousness and its relationship with the cosmos. As we delve deeper into the world of quantum mechanics, we encounter a variety of fascinating quantum entities. Photons, the particles of light, travel at an astonishing speed and exhibit properties that defy our expectations. They can be entangled, a phenomenon where two particles become linked in such a way that the state of one instantly influences the other, regardless of the distance separating them. This entanglement suggests a level of interconnectedness that transcends our classical understanding of space and time. Imagine two distant stars, their light intertwined in a cosmic embrace, communicating instantaneously across the vastness of the universe. Electrons, too, reveal the wonders of the quantum realm. These negatively charged particles orbit the nucleus of an atom, yet their paths are not fixed. Instead, they exist within a cloud of probability, often described as an electron cloud. This cloud represents the regions where an electron is likely to be found, creating a dynamic dance of possibilities. Picture a gentle breeze rustling through the leaves of a tree, where each leaf sways in response to unseen forces, mirroring the behavior of electrons in their quantum dance. The historical developments that paved the way for quantum mechanics are filled with remarkable stories of innovation and perseverance. The early pioneers faced skepticism and resistance as they proposed theories that challenged the established order. Niels Bohr, for instance, introduced the Bohr model of the atom, which proposed that electrons occupy specific energy levels rather than orbiting the nucleus in fixed paths. His ideas sparked heated debates, but ultimately laid the groundwork for our modern understanding of atomic structure. As we reflect on the journey of quantum mechanics, we encounter the brilliance of Richard Feynman, who famously remarked, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Feynman's words resonate deeply, reminding us that the beauty of this field lies in its complexity and the mysteries that remain to be unraveled. In the broader context of the universe, quantum mechanics is not merely a set of principles, but a lens through which we can view the intricate connections that bind us to the cosmos. It serves as a bridge between the microscopic and macroscopic worlds, revealing the underlying unity of all matter. The very atoms that compose our bodies are forged in the hearts of stars, where nuclear fusion occurs in an elegant dance of energy and matter. When we contemplate our place in the universe, we find ourselves intertwined with the fundamental forces that shape existence. As we continue to explore the principles of quantum mechanics, we uncover the profound implications for technology and our everyday lives. Quantum computing, for instance, harnesses the principles of superposition and entanglement to perform calculations at unprecedented speeds. Imagine a world where complex problems, once thought insurmountable, are solved in the blink of an eye, unlocking new possibilities for medicine, communication, and beyond. This technology, born from the depths of quantum theory, has the potential to revolutionize our understanding of computation and information processing. In the pursuit of knowledge, the stories of those who dared to challenge the status quo resonate deeply. The courage to explore the unknown has led to remarkable discoveries that have shaped our understanding of reality. The journey within quantum mechanics is ongoing, a vast ocean of inquiry that invites us to dive deeper into its mysteries. As we embrace the wonders of quantum mechanics, let us remain open to the questions it raises. What lies beyond the veil of our current understanding? How do the principles of quantum mechanics influence the very nature of consciousness? With each revelation, we inch closer to a profound comprehension of the universe, yet the mysteries remain tantalizingly out of reach, beckoning us to seek answers in the depths of our curiosity. In this tranquil exploration, we find solace in the knowledge that the universe is far more intricate and interconnected than our senses may perceive. The dance of particles and waves, the interplay of light and shadow, all serve as reminders of the beauty and complexity of existence. As we journey through the realms of quantum mechanics, we embark on a path that not only challenges our intellect, but also nourishes our spirit, inviting us to marvel at the wonders of the cosmos. The exploration of quantum mechanics leads us to a deeper understanding of the strange behaviors exhibited by quantum entities. These particles, while seemingly distant from our everyday experiences, are integral to the very essence of our universe. Take, for example, the concept of superposition. This principle suggests that a quantum particle can exist in multiple states at once until it is observed or measured. Imagine a spinning coin, suspended in time, embodying both heads and tails simultaneously. It is only when you catch it that it settles into one definitive outcome. This peculiar characteristic challenges our conventional notions of certainty and reality. As we reflect on the nature of superposition, we also encounter the principle of uncertainty, famously articulated by Werner Heisenberg. He proposed that certain pairs of physical properties, like position and momentum, cannot be simultaneously known with perfect accuracy. This idea introduces a fundamental limit to our understanding, suggesting that at the quantum level, the universe is inherently unpredictable. Imagine attempting to capture the essence of a fleeting moment, only to find that it slips through your fingers like grains of sand. This uncertainty forces us to reconsider how we approach knowledge and existence itself. Historically, the implications of these principles were not immediately embraced. The reactions to early quantum theories were mixed, with many scientists grappling to reconcile them with established laws of physics. Yet amid this uncertainty, a few brave souls ventured forth. One such figure was Erwin Schrödinger, who introduced the concept of the wave function, a mathematical representation that describes the probabilities of a system's various states. Schrödinger's thought experiment, famously illustrated through the paradox of a cat that is simultaneously alive and dead until observed, serves as a striking metaphor for the perplexing nature of quantum reality. It compels us to consider the fine line between existence and observation, a theme that resonates deeply within both science and philosophy. The significance of entanglement emerges from these principles, weaving a narrative of connection that transcends the limitations of space and time. When two particles are entangled, a change in one instantly affects the other, regardless of the distance separating them. This phenomenon challenges our understanding of locality, suggesting that information can be shared instantaneously across vast expanses of the universe. Imagine two dancers, performing in perfect unison, their movements intricately linked across an infinite stage. This mysterious connection hints at an underlying fabric of reality that binds all particles together, revealing the intricate web of existence. As we delve into the world of quantum entities, we cannot overlook the role of photons, the carriers of electromagnetic force, and the embodiment of light. Photons are not just mere particles, they are messengers of energy, capable of traversing the cosmos and illuminating our very existence. Their behavior, influenced by the principles of quantum mechanics, reminds us of the dual nature of reality. They can exhibit wave-like properties, creating patterns of interference, yet they can also act as discrete particles, each carrying a specific quantum of energy. Picture a beam of light filtering through the leaves of a forest, casting a mosaic of shadows and colors. This interplay of light and darkness reflects the duality inherent in the quantum realm. The explorations of quantum mechanics have not only expanded our scientific understanding, but have also ignited philosophical debates that continue to this day. The implications of these findings extend into the realms of consciousness and reality. If our observations play a crucial role in shaping the outcomes of quantum events, what does this say about the nature of consciousness itself? Are we active participants in the unfolding of reality, or mere observers in a predetermined universe? These questions linger, inviting us to ponder the profound relationship between the observer and the observed. As we journey further into the depths of quantum mechanics, we encounter the burgeoning field of quantum technology. Quantum sensors, for instance, leverage the principles of superposition and entanglement to achieve unparalleled precision. Envision a world where gravitational waves are detected with such accuracy that the ripples of space-time can be measured and understood. This technology holds promise not only for scientific advancement, but for practical applications across diverse fields, including medicine, navigation, and environmental monitoring. The stories of those who have contributed to our understanding of quantum mechanics are rich with inspiration and resilience. Consider the journey of Marie Curie, whose groundbreaking research on radioactivity laid the foundation for modern physics. Her dedication and determination in the face of adversity serve as a testament to the power of curiosity and the pursuit of knowledge. Curie once said, "Nothing in life is to be feared, it is only to be understood." Her words resonate within the framework of quantum mechanics, urging us to confront the unknown with courage and an open mind. As we contemplate the implications of quantum mechanics, we find ourselves at a crossroads of science and philosophy. The principles that govern the quantum world challenge our perceptions, urging us to reconsider what we know about reality. The dance of particles, the interplay of energy and matter, and the uncertainties that permeate existence compel us to ponder our place within this grand tapestry of the universe. In this tranquil exploration, let us remain mindful of the wonder that surrounds us. Each discovery within quantum mechanics unlocks a new door, revealing the beauty and intricacy of the cosmos. The journey is as much about understanding the universe as it is about understanding ourselves. As we continue to unravel the mysteries of quantum mechanics, we find ourselves in a profound dialogue with the universe, a conversation that invites us to embrace the unknown and celebrate the wonders that lie ahead. Chapter 2. Exploring Wave-Particle Duality Concept. Wave-particle duality represents one of the most profound concepts in the realm of quantum mechanics, a phenomenon that challenges our intuition about the nature of light and matter. Imagine a scenario where entities can simultaneously embody the characteristics of both waves and particles, shifting their behavior based on the circumstances in which they are observed. This duality is not merely a quirky aspect of quantum mechanics. It is foundational to our understanding of the universe. The significance of wave-particle duality lies in its ability to unify seemingly disparate aspects of reality. At its core, this principle suggests that quantum entities, such as photons and electrons, do not fit neatly into the classical categories of waves or particles. Instead, they exhibit properties of both, depending on how they are measured. This realization leads us to ponder deeper questions. What does it mean for something to exist as both a wave and a particle? How does this duality influence the way we perceive the world around us? Historically, the journey toward understanding this duality began with a series of groundbreaking experiments. One of the earliest and most notable was Thomas Young's double-slit experiment, conducted in the early 19th century. Young invited observers to consider light not as a stream of particles, but as a wave phenomenon. In his experiment, light was directed through two closely spaced slits, producing an interference pattern on a screen behind them. This pattern, characterized by alternating bright and dark bands, suggested that light behaves as a wave, capable of overlapping and interacting with itself. Yet, the plot thickened when experiments began to explore the behavior of light at a more fundamental level. In one remarkable instance, when light was emitted one photon at a time, the interference pattern still emerged over time, reinforcing the idea that each photon could also exhibit wave-like characteristics. This phenomenon leads us to wonder, how can a single entity produce an effect that implies collective behavior? The answer lies in the inherent nature of quantum mechanics, where probabilities reign supreme and certainty often eludes our grasp. As the 20th century dawned, another pivotal figure emerged, Albert Einstein. His work on the photoelectric effect provided critical insight into the particle aspect of light. Einstein posited that light consists of discrete packets of energy, which he termed photons. This idea complemented Young's findings, suggesting that light could manifest as both a wave and a collection of particles. Einstein famously said, "Everything should be made as simple as possible, but not simpler," a sentiment that resonates deeply in the context of wave-particle duality, where simplicity lies in embracing complexity. To further illustrate this duality, we can compare wave-like and particle-like behaviors. Waves, such as those found in water or sound, exhibit properties like interference and diffraction. When two waves meet, they can either amplify each other or cancel each other out, creating a rich tapestry of interactions. In contrast, Particles, such as marbles or grains of sand, behave in a more straightforward manner. They travel along defined paths and can collide with each other, resulting in distinct outcomes. Yet, when we observe particles at the quantum level, their behavior can seem to mimic that of waves. Consider electrons, which can be fired through a double-slit apparatus. When both slits are open, the electrons create an interference pattern, reminiscent of light waves. However, if we attempt to observe which slit the electron passes through, the interference pattern disappears, and the electrons behave like classical particles. This curious phenomenon prompts us to ask ourselves, what role does observation play in defining reality? The very act of measuring seems to compel quantum entities to choose between wave-like and particle-like behaviors, suggesting that the observer is intertwined with the observed. The duality principle extends beyond light, influencing our understanding of matter itself. Electrons, once thought to be the building blocks of atoms, also exhibit wave-like properties. This realization was notably articulated by Louis de Broglie, who proposed that matter could similarly possess wave characteristics. His hypothesis paved the way for the development of wave mechanics, a framework that would fundamentally alter the landscape of physics. De Broglie famously stated, "We must not forget that the wave nature of matter is just as real as its particle nature." In the realm of quantum mechanics, the concept of wave-particle duality invites us to envision a universe where distinctions blur and categories dissolve. Imagine particles as ripples in a vast ocean, ebbing and flowing, at times coalescing into distinct forms, yet always retaining the essence of their wave-like nature. This perspective leads to a richer understanding of the interconnectedness of all things, urging us to reconsider our place within the cosmos. As we explore the implications of wave-particle duality, we find that it resonates not only within the confines of physics but also in philosophy, prompting reflections on the nature of reality itself. Can we truly separate the observer from the observed? What does it mean for an entity to exist in a state of potentiality, waiting to be defined by measurement? These questions linger, encouraging us to engage with the mysteries that lie at the heart of existence. The duality principle, with its profound implications for both light and matter, serves as a reminder of the intricate dance of reality. As we ponder these concepts, we begin to appreciate the beauty of uncertainty and the elegance of nature's design. The universe seems to whisper secrets to us, urging us to remain curious and open-minded, for the journey into understanding is as significant as the destination itself. In this exploration, we encounter the notion of quantum superposition, where particles can exist in multiple states simultaneously until measured or observed. It is a concept that echoes the duality of light and matter, suggesting that perhaps we, too, are part of this vast interplay of probabilities. Imagine a world where your potential selves exist at once, each path shimmering with possibility, until a choice is made that collapses the wave function into a singular experience. As we reflect on the wave-particle duality, we come to realize that it encapsulates more than just scientific inquiry. It embodies a philosophical exploration of existence, perception, and the interconnectedness of all things. The wonder of the quantum world invites us to embrace the unknown, to marvel at the intricacies of life, and to ponder the profound question, what is reality if not a delicate interplay of waves and particles, of light and matter, forever inviting us to explore its depths? The legacy of wave-particle duality extends beyond the confines of physics classrooms and research laboratories. It permeates our understanding of technology, influencing innovations such as lasers, semiconductors, and quantum computing. As we harness the principles of this duality, we unlock new potentials, steering ourselves into a future where the boundaries of our knowledge continue to expand. In this realm, we find ourselves at the precipice of discovery, standing on the shoulders of giants who have paved the way. Each contribution, from Young's initial explorations to Einstein's revolutionary insights and de Broglie's transformations, weaves a rich narrative of human curiosity and ingenuity. They remind us that the universe is not merely a collection of isolated phenomena, but a cohesive whole, inviting us to explore its depths through the lens of both science and wonder. As we carry forward into this journey of understanding, let us remain mindful of the beauty inherent in uncertainty. Wave-particle duality offers a glimpse into the intricate web of existence, revealing that reality is often more complex than it appears. It encourages us to embrace the mysteries that lie ahead, to question, to seek, and to wonder as we navigate this extraordinary tapestry of life, illuminated by the shimmering light of knowledge. The exploration of wave-particle duality invites us to consider not only the nature of light and matter, but also the very framework of our understanding of reality. As we delve further into this concept, it is important to reflect on how the duality manifests in both light and matter, revealing a shared foundation that underlines the universe's complexity. Light, often viewed through the lens of its wave-like properties, also exhibits particle characteristics that cannot be ignored. Imagine a stream of photons flowing like a river, each one capable of interacting with its environment in ways that reveal both its wave nature and its particle identity. This duality becomes particularly evident when we observe phenomena, such as the Compton effect, where X-rays collide with electrons, demonstrating that light can impart momentum much like a particle would. Here, we see the delicate balance of forces at play, reminding us that what we perceive as solid boundaries between waves and particles may merely be an illusion shaped by our measurements. Similarly, electrons, which once seemed to fit neatly into the classification of particles, reveal a fascinating wave-like nature as well. This is beautifully illustrated through the phenomenon of electron diffraction. When a beam of electrons passes through a crystal lattice, it creates patterns akin to those formed by waves interacting with obstacles. This observation leads us to ponder, how can something so seemingly solid and discrete, like an electron, behave as a wave? The answer lies in the underlying quantum structure of matter, where particles are not merely points in space, but rather manifestations of a deeper, interconnected reality. The duality principle further extends its reach into the realm of quantum mechanics through the development of the Schrödinger equation, a fundamental equation that describes how quantum states evolve over time. Schrödinger's work elegantly frames the behavior of particles as a wave function, a mathematical representation that captures the probabilities of finding a particle in various states. This concept invites us to visualize particles not as fixed entities, but as dynamic entities that exist in a state of potential, oscillating between possibilities until observed. Imagine standing at the edge of a vast ocean, where each wave could represent a different potential state of a particle, crashing upon the shore of existence when measured. As we reflect on the implications of Schrödinger's equation, we encounter the idea of wave functions collapsing, an event that transforms the probabilities of various outcomes into a definitive reality. This phenomenon brings us face to face with the role of the observer in the quantum realm. When we measure a particle, we do not just passively observe, we actively shape the nature of reality itself. This realization raises profound questions about the nature of consciousness and existence. What does it mean for our perception to influence the fabric of reality? Are we mere observers? Or do we play a pivotal role in the unfolding of events around us? Throughout history, many brilliant minds have grappled with these questions, seeking to bridge the gap between the tangible and the abstract. Figures like Niels Bohr and Werner Heisenberg contributed significantly to our understanding of the philosophical implications of quantum mechanics. Bohr famously stated, "We must be clear that when it comes to atoms, language can be used only as in poetry." Such reflections on the nature of reality highlight the challenges we face in articulating the quantum world, a realm where the familiar certainties of classical physics dissolve into a symphony of probabilities. This exploration of wave-particle duality is not confined to theoretical musings. It has practical implications that resonate through our technological advancements. The principles of quantum mechanics have paved the way for innovations that redefine our everyday experiences. Lasers, which rely on the coherent wave properties of light, have revolutionized fields ranging from telecommunications to medicine. Similarly, the development of semiconductors, which harness electron behavior, has catalyzed the digital age, enabling the creation of computers and smartphones that connect us in unprecedented ways. As we stand at the intersection of science and technology, we are reminded that our understanding of wave-particle duality is not just an academic exercise. It serves as a testament to human curiosity and ingenuity, driving us to explore the unknown and harness the forces of nature for the betterment of society. The journey through quantum mechanics invites us to embrace the complexities of existence, urging us to remain inquisitive and open to the mysteries that lie ahead. Moreover, this duality reflects a deeper philosophical inquiry into the nature of existence itself. It challenges us to reconsider our relationship with the universe and the interconnectedness of all things. Just as waves ripple through water, so too do our actions and choices create echoes that resonate throughout the cosmos. What if, in our pursuit of knowledge, we find ourselves not as isolated observers, but as integral participants in a grand tapestry of life? With every question we pose and every discovery we make, we draw closer to understanding the intricate balance of wave-particle duality. It serves as a reminder that the universe is a wondrous place, rich with enigma and potential, waiting for us to explore its depths. As we embrace this journey, let us carry forward the spirit of inquiry and wonder that has propelled humanity throughout the ages. Wave-particle duality is not merely a scientific concept. It is an invitation to revel in the mysteries of existence, to seek out the connections that bind us, and to celebrate the beauty of uncertainty. Thus, as we continue to peel back the layers of reality, we find ourselves amid a vibrant interplay of waves and particles, light and matter, each revelation illuminating the path of discovery. The journey through wave-particle duality invites us to ponder our place in the cosmos and the infinite possibilities that lie before us, urging us to remain curious, engaged, and ever willing to explore the profound depths of knowledge and existence. Chapter 3. Key Experiments Demonstrating Duality. Imagine a serene moment, a quiet laboratory illuminated by soft lights, where scientists gather to witness a phenomenon that reshapes our understanding of reality. This is the setting for the double-slit experiment, a cornerstone of quantum mechanics that reveals the enchanting dance of light and matter. In its simplest form, the double-slit experiment begins with a source of light or particles directed towards a barrier with two closely spaced slits. When these entities are allowed to pass through, one might expect to see two distinct patterns on a screen behind the barrier, as would be the case with classical particles. Instead, something remarkable occurs. A series of alternating light and dark bands emerges, creating an interference pattern that resembles the ripples of a calm pond disturbed by a gentle breeze. This pattern is emblematic of wave behavior, suggesting that particles such as photons and electrons are not merely point-like entities, but rather they exhibit wave-like properties as they traverse through the slits. Imagine a wave crest and trough, overlapping and interacting, producing areas of constructive interference where the waves amplify each other, and destructive interference, where they cancel one another out. As the experiment unfolds, a fascinating question arises. What happens if we introduce a measurement device to observe which slit the particle passes through? In this scenario, the interference pattern vanishes, replaced by two distinct bands, just as one would expect if the particles were behaving like classical objects. The very act of measurement collapses the wave-like behavior into a definitive particle state. This phenomenon invites us to ponder the implications of observation in the quantum realm. As Richard Feynman eloquently stated, the only thing we can be sure of is that we will never be able to understand quantum mechanics. His words resonate deeply as we contemplate the dual nature of particles, straddling the line between the known and the unknowable. Now let us turn our attention to electrons, those fundamental building blocks of matter that also grace us with their wave-like qualities. When electrons are subjected to the double-slit experiment, they too display the same mysterious behavior. Picture these tiny entities, often regarded as particles, behaving as waves when unobserved, creating an interference pattern that fills the screen with an intricate display of light and dark bands. What does this tell us about the nature of reality? It suggests that electrons, like photons, exist in a state of probability until they are measured. Before observation, they are not confined to a single location, but rather, they occupy a space of possibilities, akin to a cloud of potential outcomes. This notion challenges our classical intuition about particles as discrete points in space. Instead, we are invited to imagine a realm where the boundaries of existence blur, where particles are not just particles, but manifestations of probability and wave-like behavior, intertwined in a delicate equilibrium. As we explore further, let us consider the behavior of photons, those enigmatic carriers of light. When subjected to the same double-slit experiment, photons reveal their own unique characteristics. When fired one at a time, a single photon will still contribute to the formation of the interference pattern over time, as if it is aware of the presence of the other photons yet to come. This raises a tantalizing question. How can a single photon, passing through the slits one at a time, still produce an interference pattern? It is as if each photon is influenced by the collective presence of its counterparts, highlighting the interconnectedness of all quantum entities. As we delve into the implications of measurement on wave-particle behavior, we uncover a profound truth. The very act of observing a quantum entity alters its state. This concept is known as wave function collapse, a phenomenon that occurs when a quantum system transitions from a state of probability to a definitive outcome upon measurement. What does this mean for our understanding of reality? It suggests that our perception plays a crucial role in shaping the existence of quantum entities. The observer and the observed are engaged in a subtle interplay, where the act of measurement influences the behavior of particles, intertwining our consciousness with the fabric of reality. Consider the words of Niels Bohr, one of the pioneers of quantum theory, who remarked, "We must be clear that when it comes to atoms, language can be used only as in poetry." This poetic approach to understanding quantum mechanics invites us to embrace the uncertainty and beauty inherent in the duality of light and matter. As we reflect upon the double-slit experiment and its implications, we find ourselves at the intersection of science and philosophy. The questions it raises are as profound as the answers it provides. What is the nature of reality? Do we create the universe with our observations? How deeply are we connected to the quantum world that underlies our existence? In the realm of quantum mechanics, where particles become waves and waves become particles, we are reminded that our understanding of the universe is ever evolving. The double-slit experiment serves as a gateway into this mysterious world, illuminating the pathways of possibility and inviting us to explore further. As we take a moment to breathe and absorb these thoughts, let us imagine the beauty of this quantum dance. Picture the waves of light and matter intermingling, creating patterns that ripple through the cosmos, evoking a sense of wonder and curiosity. In this delicate balance of observation and existence, we find a profound connection to the universe itself. The duality of light and matter is not merely a scientific curiosity, it is a reminder of our place within the grand tapestry of reality. As we continue our journey through the realm of quantum mechanics, we will uncover more layers of this intricate story, revealing the secrets that lie within the heart of existence. As we immerse ourselves in the intricacies of photon behavior within the double-slit experiment, we uncover yet another layer of understanding. When individual photons are emitted towards the slits, one may wonder how these seemingly solitary particles interact with one another to create the interference pattern. Imagine a single photon gliding gracefully through the ether, traversing the space between slits with no apparent companion, yet still somehow contributing to a collective outcome. This notion of collective influence leads us to consider the wave function, a mathematical description of a quantum system. The wave function embodies the probabilities of a particle's position and momentum, painting a picture of potentialities rather than certainties. Each photon, while traversing the slits, is described by its own wave function, and when many photons are sent through sequentially, their combined wave functions overlap, resulting in the mesmerizing interference pattern. Isn't it fascinating to think that each individual photon, in its own silent journey, participates in a grand orchestration of reality? This behavior invites us to reimagine how we perceive not only light, but also the very nature of existence itself. As Albert Einstein once remarked, "Reality is merely an illusion, albeit a very persistent one." What if our understanding of reality is shaped not just by the presence of matter, but by the very probabilities that govern its behavior? As we consider the implications of this wave-like behavior, we must also confront the paradox that arises when we attempt to measure these quantum entities. The introduction of a measurement device does more than simply observe. It forces the wave function to collapse into a definite state. Imagine this collapse as a delicate flower folding in on itself, the vibrant potentiality of its petals reduced to a singular form. This transformation raises profound questions about the nature of knowledge and existence. What does it mean for a particle to possess many potential states, only to be forced into one by the act of observation? The duality of wave and particle is further highlighted by this very phenomenon, which challenges our classical intuitions. In the quantum realm, observation is not a passive act, but an influential one, shaping the reality we perceive. Let us also reflect on the pioneering work of physicists like David Bohm, who sought to understand the implications of this wave-particle duality through his theory of pilot waves. Bohm proposed that particles are guided by a wave function that carries information about their potential paths, creating a deeper connection between the particle and the wave. This perspective inspires us to think about the universe as a symphony of interconnected waves, where each particle is but a note resonating within the larger composition of reality. As we pause to consider these ideas, we are drawn to the realization that the implications of measurement extend beyond mere physics. They touch upon the very foundations of our understanding of consciousness and reality. Are we, as observers, active participants in the unfolding of the universe? Does our perception shape the reality we inhabit? The beauty of quantum mechanics lies in this interplay of the observer and the observed, a dance that transcends the confines of classical thought. It invites us to embrace uncertainty and to recognize the limitations of our perceptions. The interference patterns created by light and matter become not just scientific phenomena, but reflections of the intricate web of existence, encouraging us to gaze deeper into the nature of reality itself. In contemplating the duality of light and matter, we may also find ourselves drawn to the work of notable figures such as Max Born, who famously noted, "The quantum mechanical description of physical reality is not a description but a probability function." This insight underscores the essence of quantum mechanics, a world defined not by certainties, but by possibilities. Imagine, if you will, the universe as an expansive canvas, where each brushstroke represents a potential outcome, each color a different possibility. As we observe, we alter this canvas, choosing which hues to emphasize and which to diminish. This artistic metaphor encapsulates the duality we have been exploring, an interplay of light and shadow, wave and particle, existence and observation. As we continue to explore these concepts, let us embrace the wonder inherent in quantum mechanics. The double-slit experiment is not merely a demonstration of scientific principles. It is an invitation to ponder the very nature of reality. The interplay between observation and existence resonates through the ages, echoing the thoughts of philosophers and scientists alike. In this gentle exploration, we find ourselves at the brink of understanding a reality that is as fluid as it is profound. We begin to appreciate that the universe is not a static arena of fixed entities, but a dynamic interplay of waves, particles, and probabilities, forever inviting us to question, to wonder, and to explore. In this soft embrace of knowledge, let us imagine the particles and waves as they weave through the cosmos. Picture them as they glide and swirl, creating patterns that ripple through the fabric of existence, resonating with the heartbeat of the universe. Each interaction, each observation, contributes to the unfolding story of reality, an eternal narrative that invites us to be both observers and participants in the grand dance of existence. As we delve deeper into these realms, we are reminded of the profound connections that bind us to the universe. The duality of wave and particle is but one thread in the intricate web of nature, a testament to the beauty and complexity of the cosmos. With each exploration, we inch closer to unraveling the mysteries that lie at the heart of existence, forever guided by the light of curiosity and the quest for understanding. Chapter 4. Mathematical Foundations of Duality. In the heart of quantum mechanics lies a mathematical framework that serves as the backbone of our understanding of duality. The intricate equations that describe this realm invite us to delve into the very essence of reality, revealing the wonders that lie beneath the surface. Let us imagine for a moment the elegance of these equations, each a key unlocking the mysteries of the universe. At the core of our exploration is the wave function, a mathematical entity that encapsulates the state of a quantum system. Visualize this wave function as a shimmering ocean, where each wave represents a different possibility, a different outcome waiting to be realized. The wave function is not merely a tool for calculation. It embodies the probabilities of finding a particle in a particular state when a measurement is made. It is a beautiful manifestation of the uncertainty principle, a reminder that in the quantum world, certainty is often an illusion. The relationship between the wave function and duality becomes particularly clear when we turn our attention to Schrödinger's equation. This fundamental equation governs the evolution of the wave function over time, painting a dynamic picture of how quantum states change and interact. Picture a serene river flowing through a landscape, its course determined by the terrain it traverses. Schrödinger's equation describes this flow, guiding the wave function as it navigates through the complexities of the quantum realm. As we contemplate Schrödinger's equation, we encounter the concept of probability amplitudes. Each wave function can be thought of as a collection of these amplitudes, each representing a potential outcome of a measurement. Imagine a vast symphony, where each note plays a role in creating a harmonious melody. The amplitudes work together, intertwining their influences to give rise to the probabilities we observe. When we perform a measurement, it is as if we are selecting a single note from this grand symphony, collapsing the possibilities into a definitive reality. The mathematical elegance of Schrödinger's equation allows us to support physical interpretations of quantum phenomena. As we consider the implications of this equation, we can see how it provides a framework for understanding the wave-particle duality that we discussed in previous chapters. Each solution to Schrödinger's equation corresponds to a specific state of the quantum system, embodying both the wave-like and particle-like characteristics that define its behavior. This duality is not a mere philosophical abstraction. It is grounded in the very equations that govern the quantum world. To illustrate the harmony between mathematics and physical reality, let us reflect on the work of notable physicists who shaped our understanding of these concepts. One such figure is Erwin Schrödinger himself, whose insights into the wave function and its implications transformed the landscape of quantum mechanics. He once remarked, "Quantum mechanics is not a description of the world, but rather a set of rules for calculating probabilities." This perspective emphasizes the role of mathematics as a guiding force, steering our understanding of the universe towards a probabilistic interpretation. As we ponder the role of the wave function and Schrödinger's equation, we may ask ourselves, how do these mathematical tools bridge the gap between abstract theory and tangible reality? The answer lies in the ability of mathematics to describe complex phenomena in a coherent manner. Through the lens of these equations, we gain insights into the behavior of particles, their interactions, and the very fabric of existence itself. Imagine standing at the edge of a vast landscape, where every contour and curve is mapped by intricate equations. The beauty of this mathematical landscape lies in its ability to reveal the underlying principles that govern the universe. Each equation, each variable, serves as a guide that helps us navigate the complexities of quantum mechanics, illuminating the path towards deeper understanding. The interplay between mathematics and physical interpretation is further enriched by the concept of superposition. In this state, a quantum system exists in multiple configurations simultaneously, much like a painter mixing colors on a palette. Each configuration contributes to the overall wave function, creating a rich tapestry of possibilities. It is through the lens of Schrödinger's equation that we see how these configurations evolve over time, shaping the probabilities that govern our observations. As we contemplate this mathematical foundation, we may wonder, what implications does this have for our perception of reality? The answers are profound. The equations of quantum mechanics challenge our classical intuitions, inviting us to reconsider what it means for something to exist. The duality of wave and particle urges us to embrace a more nuanced understanding of existence itself, one that transcends the limitations of our everyday experiences. In this realm of possibilities, the mathematical framework not only describes the behavior of particles, but also evokes a sense of wonder and curiosity. The elegance of the equations inspires us to explore the boundaries of knowledge, to seek answers to questions that have yet to be asked. Consider the role of mathematics in shaping scientific discoveries. The work of pioneers such as Niels Bohr and Richard Feynman illustrates how mathematical insights have led to groundbreaking advancements in our understanding of quantum mechanics. Their contributions underscore the importance of mathematical rigor in interpreting the phenomena we observe in the universe. As we reflect on these contributions, it becomes clear that mathematics is not merely a tool for calculation. It is a language through which we express the complexities of the cosmos. The interplay between mathematics and physical interpretation serves as a reminder that the universe is not just a collection of particles, but a symphony of interactions, governed by rules that can be elegantly expressed through equations. Let us now consider the implications of the wave function in practical scenarios. When we observe a quantum system, the wave function collapses, revealing a specific outcome from the multitude of possibilities. This phenomenon can be likened to the act of opening a book, where each page turns to reveal a new chapter in the story of existence. The mathematics of quantum mechanics provides us with the tools to understand these transitions, guiding us through the unfolding narrative of reality. As we ponder the mathematical foundations of duality, we may find ourselves contemplating the nature of reality itself. Are we merely observers in a vast, intricate play, or do we actively participate in shaping the outcomes we witness? The interplay between probability and observation invites us to explore the philosophical implications of our existence within this quantum framework. In this journey through the mathematical landscape of duality, we are reminded of the beauty that lies in the intricacies of the universe. The equations that govern quantum mechanics are not just abstractions. They reflect the profound interconnectedness of all things. As we embrace this duality, we begin to appreciate the depth of understanding that arises from the fusion of mathematics and physical interpretation. The wave function, Schrödinger's equation, and probability amplitudes all contribute to a richer comprehension of the quantum world. They remind us that beneath the surface of reality lies a complex web of possibilities waiting to be explored. Through this exploration, we unlock the potential for new discoveries and insights that can reshape our understanding of the cosmos. As we continue this journey through the mathematical foundations of duality, let us keep our minds and hearts open to the wonders that await us. The interplay of mathematics and physics invites us to embrace complexity, to seek clarity within uncertainty, and to marvel at the beauty of existence itself. As we immerse ourselves deeper into the mathematical foundations of duality, we encounter the intricate relationship between the wave function and its implications for quantum systems. The wave function acts as a bridge between the abstract world of mathematics and the tangible reality we experience. It encapsulates not just the current state of a quantum entity, but also the myriad possibilities that lie ahead, each waiting to be unveiled. Imagine this wave function as an artist's canvas, where every brushstroke represents a potential reality that could emerge from the canvas of existence. To grasp the significance of the wave function, let us consider its normalization. This concept is crucial in ensuring that the total probability of finding a particle across all possible states sums to 1. Visualize this as a delicate balance, where each possibility contributes to the overall picture of reality. When we normalize the wave function, we create a coherent framework that allows us to make sense of the probabilities inherent in quantum mechanics. It is a gentle reminder that while uncertainty reigns, there is an underlying order that governs the chaos. With the wave function firmly established, we turn our attention to Schrödinger's equation. This equation is often revered as the cornerstone of quantum mechanics, capturing the essence of how wave functions evolve over time. It can be likened to a river carving its path through a landscape, shaping the terrain as it flows. The equation illustrates how the wave function changes, adapting to the influences of external forces and interactions. In this way, Schrödinger's equation serves as a map, guiding us through the undulating currents of quantum behavior. As we reflect on the mathematical elegance of Schrödinger's equation, we might wonder, how does this equation allow us to predict outcomes with such precision? The answer lies in the relationship between the wave function and its associated energy levels. Each solution to Schrödinger's equation corresponds to a distinct energy state of the quantum system, revealing a wealth of information about the behavior of particles. Imagine uncovering hidden layers of a complex painting. Each layer, each energy level, provides insight into the dynamics of the system. The concept of probability amplitudes emerges from this framework, acting as the building blocks of our understanding. Each amplitude is tied to a specific outcome, contributing to the overall wave function. The mathematics behind these amplitudes reveals a profound truth about the nature of reality. Outcomes are not predetermined, but rather shaped by the interplay of possibilities. This insight resonates with the famous words of physicist Richard Feynman, who famously said, "The universe is not made of atoms. It is made of tiny stories." Each probability amplitude tells a story of what could be, awaiting the moment of measurement to crystallize into existence. As we explore these mathematical concepts, we can't help but draw parallels to everyday experiences. Consider the act of choosing a path on a walk. Each step forward is influenced by countless variables, weather, mood, surroundings, resulting in a unique journey. Similarly, the wave function encompasses a multitude of pathways, with probability amplitudes guiding which path is realized when we make an observation. The beauty of this analogy lies in its simplicity, illustrating how complex quantum phenomena can mirror our lived experiences. In the realm of quantum mechanics, the wave function does not merely describe a system. It reflects the interconnectedness of all things. Each wave function interacts with others, creating a rich network of possibilities. This interconnectedness is a fundamental aspect of quantum reality, underscoring the idea that no particle exists in isolation. As we navigate through this web of interrelations, we are reminded of the words of physicist David Bohm, who highlighted that, quote, "The universe is an undivided whole." This perspective invites us to appreciate the profound intricacies of the cosmos, where the mathematical language of quantum mechanics serves as a unifying force. Mathematics not only provides clarity, but also opens doors to interpretation and understanding. As we reflect on the role of mathematics in quantum mechanics, we might ask ourselves, how does this mathematical framework influence our grasp of reality? The elegance of these equations allows us to model physical phenomena with remarkable accuracy, uncovering the hidden patterns that govern the quantum world. Each equation serves as a lens through which we can observe the interplay of wave and particle, revealing the duality that lies at the heart of existence. As we continue to explore these mathematical foundations, we find ourselves drawn to the implications of wave function collapse. This phenomenon occurs when a measurement is made, causing the wave function to reduce from a state of superposition to a singular outcome. Picture it as a blooming flower that suddenly closes, revealing a specific form after the sunlight has illuminated its multitude of petals. The mathematical framework of quantum mechanics provides us with the tools to understand how this transformation occurs, allowing us to comprehend the transition from potentiality to reality. The act of measurement in quantum mechanics is not merely an observational process. It is a profound interaction that shapes the very fabric of existence. This brings to mind the philosophical inquiries surrounding the observer effect, which posits that the act of observing can influence the system being observed. Are we passive spectators in a grand cosmic play, or do we actively participate in shaping the narrative? The mathematics of quantum mechanics suggests a more intricate relationship between observer and observed, one that challenges our notions of separateness and individuality. As we reflect on these concepts, we are reminded of the words of physicist John Archibald Wheeler, who famously posed the question, "Is the universe a computer?" This provocative inquiry invites us to consider the nature of reality as a vast informational construct, where the mathematical equations serve as the code that defines the universe. Just as a computer program can generate an infinite array of outcomes from a finite set of instructions, the wave functions and equations of quantum mechanics encode the potentialities that shape our experiences. In this rich tapestry of mathematical thought, we find a sense of calm amidst the complexities of existence. The equations of quantum mechanics, while intricate and profound, invite us to explore the beauty of uncertainty and the possibilities that lie within. They reassure us that beneath the chaos, there exists an order, a delicate balance that governs the dance of particles and waves, drawing us closer to the essence of reality itself. As we continue our exploration of the mathematical foundations of duality, let us remain open to the revelations that these equations offer. The interplay of mathematics and physics serves as a guiding light, illuminating the path toward deeper understanding and newfound insights. Each equation, each wave function, beckons us to delve further into the mysteries of the universe, where the dance of duality unfolds in all its intricate splendor. Chapter 5. The Observer Effect and Measurement Problem. Imagine standing at the edge of a vast ocean, where each wave carries with it the secrets of the cosmos, whispering tales of light and shadow. This is not merely an ocean of water, but an ocean of possibility, embodying the essence of quantum mechanics. At the heart of this realm lies a concept known as the observer effect, a phenomenon that invites us to consider how our conscious act of measurement influences the very nature of reality. The observer effect in quantum mechanics suggests that the mere act of observation can alter the state of a quantum system. Picture a delicate butterfly, its wings painted with the colors of the universe, resting upon a flower. If you approach to observe it closely, the gentle flutter of its wings may change, transforming your experience. Similarly, in quantum mechanics, when we attempt to measure a system, we disturb its natural state, causing it to behave differently than it would if left unobserved. This interaction raises a profound question. Does reality exist independently of our observation, or is it shaped by our conscious presence? Consider the iconic double-slit experiment where particles, like photons or electrons, are fired toward a barrier with two slits. When unobserved, these particles create an interference pattern on a screen behind the slits, suggesting they behave like waves, simultaneously passing through both openings. This phenomenon evokes a beautiful image of waves overlapping, creating a symphony of light and dark bands. Yet, when we choose to observe which slit the particle passes through, the interference pattern collapses, and the particles behave like individual entities, creating two distinct patterns, as if they have chosen a path. This shift from wave-like to particle-like behavior is the essence of the observer effect, illustrating how our measurement alters the state of what we seek to understand. As we ponder the implications of this effect, we find ourselves at the crossroads of perception and reality. Albert Einstein, a luminary of physics, once said, "Reality is merely an illusion, albeit a very persistent one." This notion resonates deeply within the context of quantum mechanics. Our observations are not passive acts. They are active engagements that shape the fabric of what we perceive as reality. This brings us to the measurement problem, a central dilemma in quantum mechanics that further complicates our understanding. The measurement problem invites us to consider, how does a quantum system transition from a superposition of states where it exists in multiple possibilities to a single definitive outcome upon observation? Imagine a coin spinning in the air, embodying both heads and tails until it lands and reveals one face. In quantum mechanics, before measurement, particles exist in a state of superposition, where they can be in multiple states simultaneously. It is only when we measure them that they collapse into a single state. How, then, does the act of measurement dictate this transformation? Various interpretations have emerged to unravel this mystery, each offering a unique perspective on the nature of reality. The Copenhagen interpretation, one of the most widely accepted, asserts that quantum systems do not possess definite properties until they are measured. In this view, the observer plays a crucial role, collapsing the wave function into a single outcome. Picture yourself as an artist, painting on a canvas. Until the brush touches the surface, the potential for color and form exists in an infinite array of possibilities. On the other hand, the many worlds interpretation posits that all possible outcomes occur, each in its own branching universe. Imagine a tree with countless branches, each representing a different reality. In this view, every measurement leads to a branching of realities, where each possibility is realized in an alternate universe. This interpretation challenges our understanding of existence, suggesting that we are but one thread in a vast, multicolored tapestry of realities. Another intriguing perspective arises from the pilot wave theory, which introduces the idea of hidden variables guiding quantum particles along predetermined paths. This interpretation offers a deterministic view of quantum mechanics, where particles have specific trajectories, hidden from our view. It evokes an image of a river flowing through a landscape, its path shaped by unseen currents, leading to predictable outcomes, yet remaining elusive to our direct observation. As we explore these interpretations, we are invited to reflect on the nature of our observations and their impact on the world around us. How do we reconcile the act of measurement with the inherent uncertainties of quantum mechanics? This question echoes through the corridors of scientific inquiry, guiding researchers in their quest to understand the deeper fabric of reality. The influence of observation extends beyond the realm of particles. It permeates our understanding of wave-particle behavior. Imagine a serene lake, its surface reflecting the sky. When a stone is thrown into the water, ripples are created, disturbing the stillness and altering the reflection. Similarly, in the quantum world, the act of measurement disturbs the delicate balance of wave and particle states. This interplay raises further questions about the nature of existence and the role of the observer. The deeper we dive into this ocean of inquiry, the more we find ourselves pondering the profound implications of our observations. What if our very act of witnessing reality shapes it in ways we cannot fully comprehend? This idea resonates deeply with the words of physicist Niels Bohr, who remarked, "There is no quantum world. There is only an abstract quantum description." In this light, our observations may not merely reveal reality, they may construct it, inviting us to consider the power we wield as observers. As we navigate the currents of the observer effect and the measurement problem, we find ourselves at the intersection of science and philosophy. The questions we ask shape the answers we seek, and our pursuit of understanding invites a deeper engagement with the mysteries of the universe. How do we continue to explore these ideas, and what does it mean for our understanding of existence? The observer effect and measurement problem compel us to reflect on the nature of reality and our place within it. They challenge us to embrace the uncertainty that permeates the quantum realm while recognizing the artistry of our observations. Like a painter standing before a blank canvas, we are invited to engage with the world, to observe, measure, and create meaning from the tapestry of existence that unfolds before us. As we contemplate the implications of our observations, we are reminded that the universe is a dynamic interplay of possibilities, where each active measurement shapes the narrative of reality. The observer effect is not merely a scientific phenomenon, it is a profound invitation to explore the depths of existence, to question the boundaries of knowledge, and to embrace the beauty of uncertainty that lies at the core of our understanding. As we delve further into the intricacies of the observer effect, we must consider how the act of measurement not only influences the quantum state, but can also define the very nature of particles themselves. Imagine, if you will, a painter standing before a blank canvas, brush poised in hand. The moment the brush touches the canvas, color and form emerge from the void. In a similar way, when we observe a quantum system, we engage in a creative act that crystallizes potential into reality. The role of measurement is not merely a passive act of observation, but an active component in the unfolding drama of quantum phenomena. A measurement forces a particle to choose a state, which can be likened to the moment a performer steps into a spotlight, revealing their role within the grand narrative. This interaction raises profound questions. What does it mean for a quantum system to have multiple potential states? And how does our engagement with these systems shape their outcomes? The measurement problem invites us to explore various interpretations, each adding a layer of complexity to our understanding. Consider the de Broglie-Bohm theory, which suggests that particles are guided by a wave function, maintaining a deterministic trajectory. This approach offers a different perspective, suggesting that the apparent randomness of quantum events may stem from our inability to fully know the initial conditions of the system. It prompts us to wonder, are there hidden variables, unseen forces that govern the behavior of particles, much like the currents beneath the surface of a river? Another interpretation, the objective collapse theory, posits that wave functions collapse spontaneously, independent of observation. This perspective conjures an image of reality as a living entity, where events unfold and possibilities materialize irrespective of our perception. Here, the act of observation becomes merely one of many threads in a more complex tapestry of existence. Yet this raises further inquiries. What is the nature of reality in this view? And how do we reconcile the chaotic dance of particles with our experiences of order and structure? As we consider these interpretations, we are drawn into a deeper understanding of wave-particle behavior, a phenomenon that continues to captivate the minds of physicists. The duality of light and matter challenges our perceptions, compelling us to question not only how we observe, but how observation itself alters the very nature of what we are observing. It is akin to gazing into a mirror, where our reflection changes based on the angle of light and the observer's position. Imagine watching a delicate feather floating through the air. It embodies the essence of both wave and particle as it interacts with the surrounding environment. This duality is not merely an abstract concept. It has real-world implications, as evidenced by the behavior of electrons in an atom. When we probe deeper into the structure of atoms, we find that electrons do not orbit the nucleus in fixed paths, as once imagined. Instead, they exist in cloud-like distributions, a mesmerizing display of probabilities. This understanding leads us to contemplate the implications of our observations on atomic structure. How do our measurements influence the behavior of these particles? When we measure an electron's position, we disturb its wave function, collapsing it into a specific location. The act of measuring alters its trajectory, reminding us that we are not mere spectators but active participants in the quantum realm. This intertwining of observation and measurement is beautifully illustrated in the concept of quantum entanglement. Imagine two entangled particles, their states linked in such a way that the measurement of one instantaneously affects the other, regardless of the distance separating them. This phenomenon defies classical intuition, inviting us to envision a world where everything is interconnected and our actions resonate across the cosmos. As we ponder these connections, we encounter the profound implications of the observer effect, which extends beyond particles to touch the realms of consciousness and perception. How does our awareness shape our understanding of reality? Can we truly separate the observer from the observed? The words of physicist John Archibald Wheeler echo in this context. We are not just passive observers of the universe. We are active participants in its creation. This perspective invites us to reflect on our role in the unfolding narrative of existence. In this light, the observer effect becomes a mirror reflecting the nature of our engagement with the universe. It asks us to consider the interplay of intention, awareness, and experience as we navigate the delicate balance between observer and observed. As we stand at the precipice of understanding, the act of measurement transforms into a sacred dance, where each step shapes the unfolding story of reality. The measurement problem serves as a reminder of the mysteries that linger in the shadows of our understanding. It invites us to embrace the uncertainties and complexities of the quantum world, while also acknowledging the beauty of our observations. Each question we ask, each measurement we take, weaves a thread into the fabric of existence, enriching our journey through the cosmos. As we continue to explore the depths of quantum mechanics, we are compelled to keep our minds and hearts open to the wonders that lie ahead. The observer effect and measurement problem are not mere scientific puzzles. They are profound invitations to engage with the universe in a manner that honors both our curiosity and the mysteries that remain. In doing so, we may find ourselves becoming more than mere observers. We become co-creators in the ever-unfolding narrative of reality. Chapter 6. Implications for Classical Physics. In the realm of scientific understanding, classical physics has long stood as a pillar of certainty, providing a framework through which we could explain the motions of planets, the behavior of objects, and the forces at play in our macroscopic world. Yet, as we journey into the depths of quantum mechanics, we encounter a striking contrast that challenges every intuition we hold about reality. Classical physics, with its clean lines and predictable outcomes, begins to blur when faced with the strange and often bewildering phenomena that arise at the quantum level. Imagine standing in a world governed by clear rules, where every action has a predictable reaction. This is the classical perspective. A thrown ball follows a parabolic path, a planet orbits a star in a defined trajectory, and every push, pull, and interaction is accounted for within the laws of motion articulated by great minds like Newton and Galileo. However, enter the quantum realm, where particles can exist in multiple states simultaneously, and the very act of measurement alters the state of what we observe. The stark divide between classical and quantum physics thus becomes evident, as these two paradigms offer fundamentally different insights into the nature of existence. Our understanding of reality faces profound challenges when we consider the implications of quantum mechanics. Classical intuitions, which have guided humanity through centuries of discovery, seem to falter. For instance, we often think of objects as having definite properties, mass, position, and speed that can be measured and known. Yet, in quantum mechanics, particles like electrons do not possess definite properties until they are observed. Instead, they exist in a state of superposition, a term that describes their ability to occupy multiple states at once. Picture a spinning coin hovering in midair, where it is both heads and tails until it finally lands. This dance of possibilities is not just a quirky feature of quantum mechanics. It fundamentally alters how we perceive the nature of reality itself. Superposition leads us into the fascinating territory of entanglement, another cornerstone of quantum mechanics. When particles become entangled, the state of one particle is intrinsically linked to the state of another, no matter how far apart they are. Imagine two dancers, perfectly synchronized, moving in harmony despite being separated by vast distances. If one dancer twirls, the other instantly knows to follow, regardless of the space between them. This phenomenon defies classical notions of locality, suggesting that information can be shared instantaneously across great distances. Albert Einstein, who famously referred to entanglement as spooky action at a distance, grappled with its implications, as it seemed to contradict the speed limit set by the speed of light. This leads us to a deeper contemplation. If the universe indeed operates on principles of entanglement, what does that say about our understanding of determinism? Classical physics upholds a deterministic view of the universe, where every event is the result of prior causes, a cosmic clockwork of predictable outcomes. Yet, the probabilistic nature of quantum mechanics suggests a universe where events are not strictly determined, but rather influenced by a web of possibilities. This shift challenges the very foundation upon which classical physics is built, inviting questions that have lingered in the minds of physicists and philosophers alike. What if, at the core of reality, uncertainty reigns supreme? The implications are staggering. If the universe is not strictly deterministic, how do we reconcile this with our everyday experiences? Our lives are filled with moments of choice and consequence, yet quantum mechanics introduces a level of unpredictability that seems to undermine the notion of free will. Are we simply players in a grand cosmic game, or do we wield the power to shape our destinies? As we reflect on these ideas, it becomes essential to acknowledge the pioneering thinkers who have ventured into this uncharted territory. Niels Bohr, a key figure in the development of quantum theory, famously stated that an expert is a person who has made all the mistakes that can be made in a very narrow field. His willingness to embrace the uncertainties of quantum mechanics while challenging classical intuitions paved the way for a deeper understanding of the microscopic world. Consider how these concepts ripple through the fabric of our understanding. The notion of superposition, where particles can exist in multiple states, beckons us to reevaluate how we perceive reality. Imagine looking at a landscape that shifts and changes, depending on the light and angle from which you view it. Just as the landscape is not static, neither is the underlying reality of quantum mechanics. Entanglement, too, invites a sense of wonder. It reveals a universe that is interconnected, where the actions of one particle can reverberate through the cosmos, transcending the traditional boundaries of time and space. This interconnectedness prompts us to ask, are we, in some way, entangled with the universe itself? As we explore the implications for classical physics, the deterministic views we once held begin to dissolve, replaced by a tapestry of probabilities and possibilities. The universe, it seems, is not merely a machine, but a living, breathing entity, rich with connections and surprises. The elegant equations of classical physics, while still valuable for understanding many phenomena, begin to falter as we confront the strange behaviors of the quantum world. The challenges posed by quantum mechanics invite us to reconsider the very essence of reality. We are left to ponder whether our experiences of causality and predictability are mere illusions, shaped by our limited perspective. As we navigate this landscape, we find ourselves standing at the threshold of a new understanding, one that embraces uncertainty and interconnection. What does it mean to live in a universe where the rules of classical physics no longer apply? This question echoes through the corridors of scientific inquiry, urging us to explore further. The implications extend beyond the realm of physics, touching upon philosophy, consciousness, and even our understanding of existence itself. As we continue to unravel the mysteries of quantum mechanics, we realize that the journey does not end here. The interplay between classical and quantum ideas will continue to shape our understanding of the universe, inviting new questions and inspiring fresh perspectives. With each discovery, we inch closer to a more profound comprehension of the cosmos, finding beauty in the uncertainty that defines our existence. In this quest for understanding, we remember the words of Richard Feynman, who once said that the imagination of nature is far greater than the imagination of man. This sentiment encapsulates the journey we undertake as we strive to comprehend a reality that often eludes our grasp. The universe, in all its complexity, invites us to remain curious, to question, and to explore the myriad possibilities that lie before us. So, as we embrace the implications of quantum mechanics for classical physics, let us open our minds to the wonders that await. Each thought, each revelation, beckons us to delve deeper into the intricate dance of particles and waves, where reality is not a fixed entity, but a dynamic interplay of possibilities that shape our understanding of the universe. As we delve further into the implications of quantum mechanics for classical physics, we encounter the profound notion that the universe may not be the tidy, predictable entity we once envisioned. Instead, it reveals a landscape where randomness and uncertainty are woven into the very fabric of existence. To fully appreciate this shift, we must consider the implications of superposition and entanglement in light of classical intuitions about reality. Imagine, if you will, a world where the very act of observation transforms the outcome of what we observe. This idea is not merely a philosophical musing, but a cornerstone of quantum mechanics. In classical physics, observation is a passive act, one that simply reveals the state of an object. In contrast, in the quantum realm, the observer becomes an active participant, shaping the reality that unfolds. This interplay raises questions about the nature of knowledge and existence itself. Are we merely witnesses to a predetermined reality, or do we play a role in its creation? The concept of superposition challenges our understanding of how particles exist. Consider a photon, a fundamental particle of light that can be in a state of superposition, existing in multiple states simultaneously. Picture a serene lake reflecting the changing colors of the sky, where the water embodies both the calmness of the day and the turbulence of a storm. In the quantum world, particles similarly embrace a duality, residing in a spectrum of potential states until a measurement is made. This phenomenon compels us to rethink the idea of individuality in the universe. Are particles truly distinct entities? Or are they interwoven into a continuous flow of possibilities, a river of potential that defines their existence? Entanglement further complicates our classical intuitions. When two particles become entangled, they form a bond that transcends the constraints of space and time. Imagine two distant stars, seemingly isolated in the vastness of the cosmos, yet their fates entwined in an unbreakable bond. When one star flickers, the other responds, regardless of the distance that separates them. This instantaneous connection poses a challenge to classical notions of locality, where information is bound to travel through space at a finite speed. The implications of entanglement extend beyond mere curiosity. They invite us to reconsider our place within the universe. If particles can influence one another across vast distances, what does this mean for our understanding of separation and individuality? It suggests a universe that is profoundly interconnected, with strings of interaction weaving through the cosmos in ways we have yet to fully comprehend. As we reflect on these revolutionary concepts, we must also confront the repercussions for deterministic views of the universe. Classical mechanics, with its elegant equations and predictable outcomes, painted a picture of a universe governed by strict causality. Each event was a result of preceding actions, a cosmic clockwork that could, in theory, be calculated with absolute precision. Yet, the probabilistic nature of quantum mechanics introduces a level of unpredictability that disrupts this serene order. Imagine a chess game played on an infinite board, where each move creates a cascade of possibilities, branching into countless outcomes. The deterministic vision of the universe becomes a labyrinth of choices, where the outcome is not merely a product of initial conditions, but a dance of chance and potential. This realization confronts our understanding of causality, urging us to consider a universe in which uncertainty reigns. What, then, does this mean for our understanding of free will? If the universe is not strictly deterministic, how do we reconcile our sense of agency with the unpredictable nature of reality? This question lingers in the air, challenging the very foundations of our beliefs. Are we merely puppets swayed by the currents of chance, or do we possess the power to influence the unfolding of our destinies? These reflections invite us to consider the words of the eminent physicist David Bohm, who stated that the new physics gives us a new way of looking at the universe, which is not simply a collection of separate parts, but a whole. Bohm's insights encourage us to embrace a holistic perspective that transcends the limitations of classical thinking. As we navigate through these intricate concepts, we find ourselves at the crossroads of science and philosophy. The implications of quantum mechanics resonate not only within the realm of physics, but also echo through our understanding of consciousness, reality, and existence itself. The universe becomes a canvas painted with uncertainty, inviting us to explore the depths of possibility and the threads that bind us to one another. What if, as we contemplate these ideas, we embrace the beauty of uncertainty? The universe, in all its complexity, offers us a rich tapestry of connections and interactions. Rather than viewing randomness as a flaw, we might consider it a necessary component of a vibrant and dynamic reality. As we venture further into the implications of classical physics, we must remain open to the profound changes that these quantum revelations inspire. The journey into the quantum realm does not conclude with a neat resolution. Instead, it unfolds as an ongoing exploration that reshapes our understanding of the cosmos. Each discovery serves as a stepping stone, guiding us toward a more nuanced awareness of the universe's intricacies. The interplay between classical and quantum mechanics fosters a sense of wonder, urging us to remain curious and engaged. How might this evolving understanding of reality influence our daily lives? As we embrace the interconnectedness of all things, we may find new pathways to cultivate compassion, empathy, and awareness, enriching our experience in a world that is anything but ordinary. In the end, the implications of quantum mechanics for classical physics invite us to embark on a journey of discovery that transcends the boundaries of traditional thought. Each concept we explore serves as a reminder of the beauty and mystery that lie at the heart of existence, encouraging us to remain open to the endless possibilities that await. Chapter 7. Philosophical Perspectives on Duality. The exploration of wave-particle duality extends beyond the realm of physics, inviting philosophical inquiries that challenge our conception of reality. Imagine standing at the crossroads of existence, where the boundaries of being and non-being blur, revealing a profound interplay between light and matter. This duality, a cornerstone of quantum mechanics, raises intriguing questions about the nature of reality itself. What does it mean when a particle can act as both a wave and a particle? How does this fundamental aspect of the quantum world reshape our understanding of existence? Philosophical implications of wave-particle duality echo through the ages, prompting thinkers to ponder the very essence of reality. The idea that something can embody two seemingly contradictory states leads us to reconsider the categories through which we interpret our experiences. This dual nature suggests that the universe may not fit neatly into our established frameworks. Instead, It compels us to entertain the notion that reality is more fluid, more complex than our conventional beliefs allow. At the heart of this dialogue lies a tension between realism and instrumentalism. Realism posits that the world exists independently of our observations, asserting that the properties of particles and waves are intrinsic to them. This perspective champions the idea that there is a concrete reality waiting to be discovered, a realm governed by laws that transcend human perception. Yet, juxtaposed against this, instrumentalism presents a different viewpoint, suggesting that theories and models in science serve merely as tools for prediction rather than reflections of an absolute reality. Instrumentalists argue that our understanding of the universe is shaped significantly by our experiences and measurements, which are inherently subjective. As we contemplate these philosophical positions, consider the implications of duality on our grasp of reality. If particles can exist in both wave and particle states, how does this inform our understanding of existence itself? Does it suggest that the universe is less about fixed truths and more about dynamic interactions? The duality inherent in quantum mechanics may point toward a reality that is not only more expansive, but also more interconnected. Each observation we make is not merely a window into a static world, but rather a brushstroke on the canvas of existence. Prominent philosophers of science have weighed in on these questions, enriching the discourse surrounding quantum mechanics. Niels Bohr, a pivotal figure in the development of quantum theory, famously remarked, "We must be careful not to confuse the map with the territory." This statement serves as a reminder of the distinction between our scientific models and the complexities of the universe they seek to describe. Bohr's insistence on the complementarity principle underscores the idea that wave and particle aspects are not contradictory, but rather complementary facets of a unified reality. His perspective invites us to embrace ambiguity and complexity, allowing for a richer understanding of the quantum realm. Another notable philosopher, Werner Heisenberg, introduced the uncertainty principle, which further complicates our understanding of reality. Heisenberg suggested that the more precisely we measure one property of a particle, such as its position, the less precisely we can know another, such as its momentum. This inherent uncertainty challenges the traditional notion of an objective reality, suggesting instead that our attempts to pin down the essence of particles are constantly thwarted by the limitations of measurement. It raises the question, if certainty is an illusion, what does this mean for our pursuit of knowledge? Consider the implications of Heisenberg's ideas on our perception of duality. When we acknowledge the limits of our measurements, we begin to see that our understanding of particles and waves cannot be divorced from the act of observation. This leads us to a philosophical crossroads. Are we merely passive observers of a detached reality, or are we active participants in shaping the very nature of existence? The interplay between the observer and the observed opens up a myriad of possibilities, suggesting that reality itself might be a collaborative creation. As we reflect on these philosophical perspectives, it becomes evident that duality is not merely a scientific curiosity, but a profound invitation to question our assumptions about reality. The wave-particle duality encapsulates a deeper truth about the interconnectedness of existence, urging us to reconsider the boundaries we impose on our understanding. Can we allow ourselves to embrace uncertainty and ambiguity, recognizing that they may be essential to the fabric of reality? In this philosophical landscape, the thoughts of philosophers such as Albert Einstein resonate deeply. While Einstein famously struggled with the implications of quantum mechanics, he acknowledged the importance of duality in shaping our understanding of the universe. His assertion that God does not play dice with the universe reflects a desire for a deterministic reality, yet the very nature of wave-particle duality challenges such notions. This paradox invites us to explore the limits of our understanding, and to consider that perhaps the universe operates on principles that elude our conventional interpretations. The engagement with duality serves as a bridge between science and philosophy, enriching both disciplines as they grapple with the nature of existence. As we navigate these waters, we can appreciate that the dialogue is ongoing, evolving with each new discovery. The insights garnered from wave-particle duality encourage us to expand our horizons, to question, and to wonder about the universe in which we reside. Imagine a world where the lines separating opposing forces are softened, where light and matter coexist in a delicate balance. This vision challenges us to rethink not only the fundamentals of physics, but also the very essence of our existence. As we embrace the complexity of duality, we may find ourselves more attuned to the mysteries of the cosmos, open to the possibilities that lie beyond our immediate perception. In this context, the philosophical implications of wave-particle duality serve as a reminder of the beauty and intricacy of existence. They invite us to reflect on our place within the universe and to acknowledge that the pursuit of understanding is a journey fraught with both clarity and confusion. Each revelation leads to new questions, urging us to explore the depths of reality more profoundly, and reminding us that the answers we seek may ultimately reside in the spaces between certainty and uncertainty. Let us carry these reflections forward as we continue to explore the rich tapestry of existence, allowing the insights gained from duality to illuminate our path. As we ponder the nature of reality, may we remain open to the wonder and complexity that define our understanding of the universe, embracing the duality that resides within us all. The conversation around realism and instrumentalism in the context of wave-particle duality invites us to reflect on the very nature of knowledge and truth. As we traverse this philosophical terrain, it becomes clear that our understanding of reality is not simply a matter of uncovering facts, but rather a complex interplay of interpretation and experience. Imagine exploring a vast library, where each book represents a theory or model, each filled with narratives that describe our understanding of the universe. Some may embrace realism, asserting that these books contain the ultimate truths about existence. Others might lean toward instrumentalism, suggesting that these narratives are merely useful fictions, guiding us through the intricacies of life without necessarily revealing the underlying reality. This dichotomy brings to light an intriguing question. How do we discern what is real? The notion of wave-particle duality serves as a poignant example of this struggle. In a world where entities can embody two states simultaneously, how do we determine which state is the true nature of that entity? This uncertainty challenges the foundations of realism, inviting a re-evaluation of how we perceive and interpret scientific theories. Consider the implications of duality on our understanding of consciousness and perception. As we engage with the quantum world, we find ourselves grappling with a deeper realization that our observations shape the reality we experience. The act of measurement is not a passive endeavor. It actively transforms the landscape of existence. This leads us to ponder, are we the architects of our reality, or are we merely uncovering a pre-existing structure? Prominent philosophers such as Thomas Kuhn have influenced the discourse on scientific paradigms, suggesting that our understanding of reality is shaped by the frameworks we adopt. His concept of paradigm shifts illustrates how scientific revolutions can alter our perception of truth. When we encounter the duality of waves and particles, we are faced with a potential paradigm shift, one that challenges the very essence of our scientific models and perceptions. Kuhn's thoughts evoke a sense of wonder about the fluidity of knowledge, prompting us to consider how much of our understanding is contingent on the prevailing paradigm of the moment. As we delve deeper into the philosophical implications of duality, we encounter the reflections of contemporary thinkers like Michel Foucault, who emphasize the relationship between knowledge and power. Foucault asserts that knowledge is not simply a reflection of reality, but a construct that shapes our understanding of existence. This perspective resonates powerfully with the discourse on duality, as it suggests that the frameworks we use to interpret wave-particle duality may influence how we perceive the nature of reality itself. As we engage with duality, we are not just passively receiving knowledge, we are actively participating in the construction of meaning. In this landscape, duality urges us to embrace a more nuanced understanding of existence. It invites us to explore the interconnectedness of all things, and to recognize that our perceptions are shaped by a myriad of factors, including our experiences, beliefs, and cultural contexts. The interplay of wave and particle reflects a broader truth about the universe, that it is not a rigid structure, but a dynamic, evolving tapestry of relationships. The philosophical implications of wave-particle duality extend to our understanding of time and space as well. In the quantum realm, the traditional notions of causality and determinism begin to blur. Imagine a river flowing through a landscape, where every bend and turn represents a choice or an event. In classical physics, the course of the river follows a predictable path. However, in the quantum world, the river may split into multiple tributaries, each representing different possibilities and outcomes. This fluidity challenges our understanding of time as linear, prompting us to consider the idea that time itself may be more intricate and multifaceted than we have previously imagined. The reflections of philosophers like Alfred North Whitehead further enrich this discourse. Whitehead proposed that reality consists of a series of interconnected events rather than static objects. This perspective aligns beautifully with the concept of wave-particle duality, emphasizing that the essence of existence is found in the relationships between entities, rather than in their isolated states. When we consider duality through this lens, we begin to see a universe that is alive, pulsating with possibilities, where the very act of observation shapes the unfolding narrative of reality. As we ponder these philosophical perspectives, let us not lose sight of the beauty embedded within the complexity of duality. It is a reminder that our quest for understanding is an ongoing journey, one that encourages us to remain curious and open-minded. The interplay of wave and particle serves as a metaphor for our own experiences, where we often oscillate between different states of being, between certainty and uncertainty, clarity and confusion. In this grand exploration, we must ask ourselves, how can we cultivate a deeper appreciation for the richness of existence? How can we embrace the duality that resides within us and around us? By fostering a mindset that values exploration over dogma, we can navigate the mysteries of the universe with grace and humility. This journey encourages us to remain engaged with the questions that arise, celebrating the interplay of perspectives that enrich our understanding. As we continue to reflect on the philosophical implications of wave-particle duality, we find ourselves standing at the precipice of discovery, where each insight becomes a stepping stone toward a deeper comprehension of reality. The echoes of these thoughts resonate within us, urging us to embrace the uncertainty and wonder that define our existence. In this journey, we may find that the duality of waves and particles reflects not only the nature of the universe, but also the complexities of our own lives, inviting us to explore the boundless possibilities that lie ahead. Chapter 8. Applications of Wave-Particle Duality. In the realm of quantum mechanics, where the fabric of reality weaves together the ethereal and the tangible, wave-particle duality serves as a cornerstone for emerging technologies that promise to reshape our future. Imagine harnessing the very principles that govern the microscopic world to create machines that can process information at unprecedented speeds. This is the essence of quantum computing, a field that not only thrives on the dual nature of particles, but also leverages it to unlock the potential of vast computational power. Quantum computers operate using qubits, which, unlike classical bits that exist in a state of either 0 or 1, can exist in a superposition of both states simultaneously. Picture a spinning coin suspended in the air, representing a state where it has not yet decided if it will land on heads or tails. This unique property allows quantum computers to perform calculations at speeds that would be unimaginable with traditional computing systems. This brings us to the question: how can something so small, so seemingly inconsequential, lead to breakthroughs in fields ranging from cryptography to drug discovery? One striking example of this potential lies in the work of scientists like David Deutsch, who first proposed the idea of a universal quantum computer. Deutsch envisioned a machine that could simulate any physical process. harnessing the wave-particle duality of quantum mechanics to solve problems that are currently insurmountable. Imagine a world where complex simulations of molecular interactions could lead to the rapid development of new medications, or where the intricate patterns of financial markets could be analyzed in a fraction of the time it takes today. This promise of quantum computing brings with it a sense of wonder and excitement as we begin to glimpse the possibilities that lie just beyond the horizon. The impact of wave-particle duality extends beyond computing, reaching into modern electronics and photonics. Consider the devices we use every day: smartphones, televisions, and various gadgets that have become integral to our lives. The very principles that govern the behavior of photons and electrons enable the functioning of these technologies. In semiconductors, for instance, the duality of electrons allows them to behave both as particles, flowing through materials, and as waves, creating interference patterns that underpin their conductive properties. This wave-particle interplay is vital in the development of lasers, which have revolutionized communication and various industries. Picture a laser cutting through darkness, its coherent light a manifestation of photons acting in unison, each embodying both wave-like and particle-like qualities. This duality enables lasers to produce precise beams of light, with applications ranging from medical procedures to high-speed data transmission. Furthermore, the field of photonics, where light is manipulated and harnessed, relies heavily on the principles of wave-particle duality. Imagine the potential for innovations in data transfer speeds and energy efficiency, as researchers explore the quantum properties of light. As we stand on the brink of a new era in electronics, the implications of wave-particle duality offer a tantalizing glimpse into what the future may hold. One of the most profound applications of this duality lies in the realm of medical imaging techniques. The ability to visualize the intricate workings of the human body has transformed diagnostics, allowing for earlier detection and treatment of diseases. Techniques such as magnetic resonance imaging and positron emission tomography rely on quantum principles to generate images with remarkable clarity. Consider magnetic resonance imaging, where the behavior of atoms in a magnetic field provides insights into our internal structures. The nuclei of certain atoms resonate when exposed to radio frequency pulses, creating signals that can be converted into detailed images of tissues and organs. This process hinges on the quantum mechanics of nuclear spins, illustrating how the dual nature of particles can be harnessed for the benefit of human health. Positron emission tomography, on the other hand, utilizes the particle aspect of photons to reveal metabolic processes in the body. By injecting a small amount of radioactive material, researchers can observe the emitted positrons as they collide with electrons, leading to the production of gamma rays. These rays, behaving as particles, carry crucial information about the body's inner workings, guiding physicians in making informed decisions about patient care. As we explore the future of technology influenced by quantum principles, we can only imagine the possibilities that lie ahead. The applications of wave-particle duality are not limited to the realms of computing and imaging. They reach into the very fabric of our daily lives, shaping how we understand and interact with the universe. What if we could develop quantum sensors that surpass the limits of classical measurements, providing unparalleled accuracy in detecting gravitational waves or environmental changes? The implications would be profound, extending our capabilities in science and exploration. Envision a world where quantum principles enhance our understanding of complex systems, from climate modeling to astrophysics. The ability to simulate and analyze these intricate networks could lead to breakthroughs in sustainability, energy production, and even our grasp of the cosmos itself. As we stand at this intersection of science and technology, the narrative woven by wave-particle duality continues to unfold. Each discovery, each advancement, beckons us to reflect on the possibilities that arise when we embrace the dual nature of reality. The journey into this quantum realm not only promises to enhance our technological landscape, but also invites us to reconsider our place within the universe as active participants in a dance of light and matter. With each step forward, we grasp the power of wave-particle duality, a guiding principle that inspires innovation and discovery. As we imagine the myriad applications yet to be realized, we find ourselves on the cusp of an era defined by understanding, exploration, and transformation. The beauty of quantum mechanics lies not only in its complexity, but in its ability to illuminate the path toward a future that once seemed distant and unattainable. As we explore the vast landscape of wave-particle duality, we find ourselves at the intersection of technology and medicine, particularly in the realm of medical imaging techniques. The ability to visualize the intricate workings of the human body has always been a pursuit of paramount importance, enabling early detection and effective treatment of a multitude of diseases. Imagine being able to peer inside the human body, to see the dance of cells and organs in motion, revealing secrets that were once hidden from sight. This is the promise of medical imaging, where quantum principles play a vital role. Magnetic resonance imaging, or MRI, stands out as one of the most significant advancements in this field. At its core, this technique relies on the principles of quantum mechanics to create detailed images of our internal structures. Picture a serene environment where patients lie comfortably within a large machine surrounded by the soft hum of technology. As they relax, the machine employs a powerful magnetic field to align the nuclei of hydrogen atoms within their bodies. When exposed to radio frequency pulses, these nuclei resonate, emitting signals that the MRI machine captures to construct vivid images of soft tissues. This process, deeply rooted in the concept of wave-particle duality, exemplifies how understanding the quantum behavior of particles can lead to transformative technologies that enhance our health and well-being. In a different vein, positron emission tomography, or PET scans, utilizes the particle aspect of photons to provide insights into metabolic processes. Imagine a scenario where a physician injects a small amount of a radioactive tracer into a patient. This tracer, designed to mimic naturally occurring substances in the body, emits positrons that collide with electrons, generating gamma rays. These rays, behaving as particles, carry critical information about how organs and tissues are functioning. As the gamma rays travel through the body, they are detected by the PET scanner, which constructs images that reflect not just the structure, but also the function of the body's systems. This technique highlights the essential role of wave-particle duality, as it intricately blends the particle nature of emitted radiation with the wave-like behavior of the signals detected. The applications of wave-particle duality extend far beyond the current landscape of medical imaging. As we gaze into the future, we can envision technologies that harness these quantum principles in unprecedented ways. Imagine the development of quantum sensors that could detect minute gravitational waves, allowing scientists to explore cosmic events with a level of precision previously thought impossible. These sensors would leverage the unique properties of quantum mechanics, bringing forth a new era of exploration in fields such as astrophysics. Moreover, consider the potential for advancements in renewable energy sources through quantum principles. The interplay between light and matter could lead to more efficient solar cells that outperform current technologies. Imagine solar panels that can absorb a broader spectrum of light, converting it into energy with remarkable efficiency. Such innovations could revolutionize our approach to energy production, addressing pressing global challenges while promoting sustainability. As we contemplate these future technologies, we find ourselves drawn to the question, how will our understanding of wave-particle duality shape the next generation of scientific exploration? The answers lie in the collaborative efforts of researchers and innovators who are committed to pushing the boundaries of what is possible. The legacy of pioneers in the field, such as Richard Feynman, who once remarked on the beauty of nature's underlying principles, continues to inspire a new generation of thinkers. Their work not only builds upon the foundation of quantum mechanics, but also opens doors to realms yet unimagined. In the realm of communications, the principles of wave-particle duality are poised to redefine how we connect and share information. Quantum communication technologies, which utilize the properties of entangled particles, promise to provide secure channels of communication that are theoretically impervious to eavesdropping. Picture a world where information is transmitted instantaneously across vast distances, safeguarded by the very principles that govern the quantum realm. This leap forward could reshape industries, from finance to healthcare, enhancing the safety and efficiency of data exchange. Furthermore, the future may see the emergence of quantum-enhanced imaging techniques that surpass the limitations of current modalities. Imagine a world where we can visualize biological processes in real time, observing cellular interactions as they unfold. Such advancements would not only advance our understanding of health and disease, but could also lead to breakthroughs in personalized medicine, tailoring treatments to the unique genetic makeup of individuals. As we traverse this landscape of possibilities, we are reminded of the profound implications of embracing the dual nature of reality. Wave-particle duality is not merely a concept confined to the realm of physics. It is a guiding principle that fuels innovation and discovery in various domains. The merging of scientific inquiry with technological advancement presents an opportunity to redefine our relationship with the universe, inviting us to explore the delicate balance between observation and existence. In this unfolding narrative, we are called to remain curious and open-minded, considering how the lessons gleaned from quantum mechanics may illuminate our path forward. As we stand at the threshold of a new era, the applications of wave-particle duality inspire us to imagine a future rich with potential and possibility. Embracing these dual aspects of nature fosters a spirit of exploration and discovery as we seek to understand the very essence of reality and our place within it. Chapter 9. Quantum Field Theory and Beyond. Imagine stepping into a realm where the very essence of reality is intertwined with the dance of energy and information, a domain known as quantum field theory. This theory transcends the boundaries of classical physics, offering a rich tapestry of understanding regarding the fundamental forces and particles that shape our universe. At its heart lies the concept that every particle is an excitation of an underlying field, much like ripples on the surface of a lake. Each field is a manifestation of a particular type of force, whether it be electromagnetic, strong, or weak, each contributing to the grand symphony of existence. In this context, wave-particle duality takes on new dimensions. Picture a universe where particles do not merely exist as isolated entities, but as manifestations of vibrational patterns within their respective fields. When we observe a photon, for instance, we are not merely witnessing a particle darting through space. We are engaging with a pulse of energy resonating within the electromagnetic field. This duality illustrates how particles can manifest as both localized entities and spread out waves, depending on the circumstances of observation. It poses a captivating question. How does our perception shape the very nature of what we observe? The standard model of particle physics emerges as an elegant framework within quantum field theory, unifying the understanding of the fundamental forces of nature. Envision it as a complex yet harmonious structure that categorizes all known elementary particles and their interactions. The electrons that whirl around atomic nuclei are but one part of this intricate design, where quarks combine to form protons and neutrons, the very building blocks of matter. Each particle is governed by specific fields, and these interactions are mediated by force carrier particles, such as photons for electromagnetic force and gluons for the strong force. Renowned physicist Richard Feynman once said, "The universe is not only queerer than we suppose, but queerer than we can suppose." This captures the essence of the standard model, which reveals a universe that is both intricate and bewildering. The model describes particles in terms of their properties, such as mass and charge, yet it also raises profound questions about the very nature of these properties. Are they inherent traits, or are they merely the expressions of deeper underlying mechanisms? As we consider the implications of the standard model, we must acknowledge its limitations. Despite its success in describing a vast array of phenomena, it leaves questions unanswered. Dark matter and dark energy, which constitute a significant portion of the universe, elude its grasp. What lies beyond the standard model? How might future research unveil new layers of complexity in our understanding of the cosmos? The quest for answers drives contemporary physicists toward innovative directions in quantum research. Scientists are exploring the potential of unifying quantum mechanics with general relativity, the theory that governs the macroscopic world of gravity. This pursuit aims to forge a theory of everything, a comprehensive framework that seamlessly integrates the quantum realm with cosmic phenomena. Imagine the exhilaration of discovering a theory that could elegantly explain the behavior of black holes while detailing the interactions of subatomic particles. Another exciting frontier lies in the realm of quantum computing. The principles of quantum mechanics, particularly superposition and entanglement, have the potential to revolutionize how we process information. Picture a future where quantum computers can solve complex problems in seconds, problems that would take classical computers millennia to unravel. This leap forward promises breakthroughs in fields ranging from cryptography to material science, reshaping our technological landscape. Moreover, the exploration of quantum entanglement invites us to reconsider our notions of locality and separateness. Imagine particles that, once entangled, remain connected regardless of the distance separating them. This phenomenon challenges our understanding of space and time, suggesting that the universe may be more interconnected than we perceive. What implications does this have for our understanding of reality? How might our perception shift if we embrace a universe where connections transcend traditional boundaries? As we journey through the landscape of quantum field theory and its implications, we see a vivid interplay of ideas shaping our understanding of the universe. Each discovery adds a new layer to our comprehension, inviting us to gaze deeper into the fabric of existence. The questions raised by quantum mechanics do not merely seek answers. They invite us to explore the very nature of reality, encouraging a sense of wonder and curiosity. How will the unfolding narrative of quantum research inspire future generations to explore the mysteries that lie ahead? Let us pause for a moment and reflect on the profound implications of our findings. The world of quantum field theory is not merely an abstract domain. It is a living, breathing exploration of the universe that surrounds us. Each particle, each field, contributes to the grand narrative of existence, echoing the sentiments of pioneers who have journeyed before us. As we continue to unveil the secrets of the cosmos, we find ourselves standing on the shoulders of giants, peering into the depths of reality with renewed curiosity. What great discoveries await us in the realms beyond? Each question leads to new inquiries, beckoning us to embrace the unknown. The beauty of quantum research lies in its ability to inspire awe and wonder, serving as a reminder of our place within this vast and intricate universe. As we delve further into these mysteries, let us carry with us the spirit of exploration and the joy of discovery, igniting a passion for understanding that transcends the boundaries of time and space. In this ever-evolving landscape, where the lines between the known and the unknown blur, the journey of quantum field theory continues to unfold. It is a journey filled with possibilities, urging us to seek knowledge, to question, and to marvel at the intricate dance of the universe. Each step we take brings us closer to unveiling the profound truths that lie at the heart of existence, illuminating the path ahead with the promise of discovery and understanding. As we traverse further into the fascinating world of quantum field theory, we encounter a multitude of intriguing developments that beckon our curiosity. Among these are the principles that govern the interactions between particles, giving rise to what we refer to as symmetries. Imagine symmetries as the graceful patterns that underlie the behavior of particles, akin to the way a well-composed piece of music flows harmoniously. These symmetries, which can be observed in the conservation of energy, momentum, and charge, reveal deeper truths about the nature of the universe. One of the most compelling aspects of these symmetries is the concept of gauge invariance. This principle posits that certain physical phenomena remain unchanged under specific transformations. Picture this as the different shades of a color. Each shade may appear distinct, yet they are all variations of the same fundamental hue. Gauge invariance is a linchpin in the formulation of the Standard Model, ensuring that the laws of physics remain consistent regardless of the observer's perspective. Consider the work of physicist Yang Chen-Ning and Robert Mills, who pioneered gauge theory. Their insights laid the foundation for understanding the strong and weak nuclear forces, illuminating the intricate connections between particles and fields. Their contributions exemplify how scientific inquiry often leads to unexpected revelations about the universe. As we delve deeper into particle interactions, we must also confront the phenomenon of spontaneous symmetry breaking. Imagine a perfectly balanced top spinning in place, a symbol of stability. However, upon losing energy, it wobbles and eventually falls to one side, breaking its symmetry. In the quantum realm, this principle explains how particles acquire mass. The Higgs field, an omnipresent energy field, acts as a medium through which particles gain mass as they interact with it. This pivotal discovery, heralded by the detection of the Higgs boson, reshapes our comprehension of mass in the universe, inviting us to ponder, how does this invisible field manifest its influence on the visible world? The Higgs mechanism serves as a bridge connecting the abstract and the tangible. It reveals that mass is not merely an intrinsic property of particles, but rather a result of their interaction with a pervasive field. This revelation encourages us to reconsider our understanding of reality, prompting questions about what lies beneath the surface of the physical world. In addition to mass, the quantum realm also introduces us to the fascinating concept of quantum fluctuations. These fluctuations can be likened to the gentle ripples on a calm lake, where even in a state of apparent tranquility, fluctuations occur at a microscopic level. Quantum fluctuations give rise to temporary particles that pop in and out of existence, illustrating the dynamic nature of the vacuum. This intriguing notion challenges our traditional views of emptiness, suggesting that even in the absence of matter, activity persists. Imagine a universe where the very fabric of space is alive with activity, where virtual particles continuously emerge and vanish, contributing to the richness of the cosmos. This idea resonates with the principle of vacuum energy, which suggests that the vacuum is not an empty void, but a bustling sea of potential. The implications of these fluctuations extend beyond the realm of theory, influencing phenomena like Hawking radiation, the process through which black holes emit energy. As we embrace the complexities of quantum field theory, it becomes increasingly clear that our understanding is continually evolving. The exploration of quantum gravity represents one of the most exhilarating frontiers in modern physics. Picture a realm where the laws of quantum mechanics intertwine with Einstein's general relativity, governing the behavior of space-time itself. This pursuit seeks to unravel the mysteries surrounding black holes and the origins of the universe, challenging us to contemplate the very nature of existence. What if the fabric of space-time itself is quantized, much like matter at the atomic level? This notion evokes a sense of wonder, as we envision a universe where space-time is not a smooth continuum, but a discrete entity composed of a myriad of interwoven threads. This perspective invites us to ponder the implications for our understanding of time and space, urging us to question the very essence of reality. In tandem with these theoretical explorations, researchers are also delving into the practical applications of quantum field theory. Quantum technologies are beginning to take shape, transforming industries and enhancing our everyday lives. From quantum sensors that detect minute changes in the environment, to quantum communication systems that promise secure information transfer, the potential applications are vast. Picture a future where quantum technologies seamlessly integrate into our daily routines, enhancing our capabilities and expanding our horizons. This prospect is not merely a figment of imagination. It is a testament to the power of scientific inquiry and innovation. As we witness the unfolding of these advancements, we cannot help but marvel at the interconnectedness of knowledge and the boundless possibilities that lie ahead. Yet, as we stand on the precipice of these discoveries, we must also reflect on the ethical implications of our advancements. The profound power of quantum technologies raises questions about responsibility and the impact of our choices on society. How do we ensure that these innovations serve the greater good? This inquiry emphasizes the importance of interdisciplinary dialogue, merging science with ethics to create a future that is both enlightened and compassionate. In this ongoing narrative of quantum field theory, we find ourselves drawn into a web of inquiry that transcends mere academic pursuit. Each discovery invites us to engage with the universe in a new way, bridging the gap between science and philosophy. As we contemplate the future directions in quantum research, we can envision a landscape bustling with potential, a landscape where the mysteries of the cosmos beckon us to explore further, to question more deeply, and to revel in the beauty of discovery. With every question we pose, we inch closer to understanding the intricate dance of existence, forever inspired by the wonder of the quantum realm. Each moment spent in contemplation unveils new layers of complexity, urging us to embrace the unknown as we embark on this extraordinary journey together. Chapter 10: The Future of Quantum Mechanics and Duality. In the expansive cosmos of quantum mechanics, researchers face a multitude of challenges that test the limits of our understanding. Imagine standing at the edge of a vast ocean, where each wave symbolizes a question yet to be answered. One of the significant hurdles lies in the interpretation of quantum mechanics itself. The very nature of reality at the quantum level remains a source of debate among scientists. How can particles exist in a state of probability, only to collapse into a defined state upon observation? This enigma continues to provoke thought and ignite discussions, as physicists strive to unravel the complexities of the quantum world. As we explore these challenges, we encounter the quest for a unified theory of physics. Picture an intricate puzzle, with each piece representing different aspects of our understanding: gravity, electromagnetism, the strong and weak nuclear forces. The dream of a grand unification theory aims to connect these seemingly disparate forces into a cohesive framework, offering a deeper comprehension of the universe. This endeavor has captivated the minds of visionaries like Albert Einstein and Stephen Hawking, who sought to weave together the threads of mathematics and physics to illuminate the underlying structure of reality. Einstein famously remarked that the most incomprehensible thing about the universe is that it is comprehensible. This quest for coherence resonates deeply, as each new discovery reflects our relentless pursuit of knowledge. In this search for unity, researchers are delving into the duality of particles, striving to unlock potential breakthroughs in understanding how wave-particle duality manifests in various contexts. Imagine the dual nature of light, a phenomenon that can be both a wave, spreading across space, and a particle, striking surfaces with pinpoint precision. This duality is not merely a theoretical curiosity. It has profound implications for our grasp of the universe. As scientists investigate the nature of quantum entanglement and the behavior of particles at extreme conditions, they inch closer to insights that could redefine our perceptions of reality. Consider the implications of discovering a more profound understanding of duality. How would our grasp of the universe transform if we could reconcile the behavior of particles across different states? The potential to understand how particles interact, not just as independent entities, but as interconnected components of a broader system, opens doors to revolutionary advancements in technology and science. This exploration encapsulates the spirit of inquiry that has driven scientists through the ages, from the early pioneers of quantum theory to the modern-day researchers, pushing the boundaries of current knowledge. New technologies play a pivotal role in advancing quantum studies, acting as both tools and catalysts for discovery. Envision a laboratory filled with cutting-edge equipment, where scientists manipulate quantum systems with precision, Quantum computers, leveraging the principles of superposition and entanglement, hold the promise of solving complex problems that are currently intractable for classical computers. Picture a future where these machines revolutionize fields such as cryptography, materials, science, and pharmaceuticals, transforming our approach to challenges we face. Moreover, advancements in experimental techniques have enabled physicists to explore phenomena at unprecedented levels of detail. Consider the use of lasers in experiments that probe the behavior of atoms and molecules, allowing researchers to observe interactions with remarkable clarity. As we develop stronger, more sophisticated tools, we gain insights that were once thought to be beyond our reach. This interplay between technology and theory fosters a vibrant ecosystem of research, where each breakthrough illuminates the path ahead. As we ponder the future of quantum mechanics, we must also reflect on the philosophical dimensions that accompany these scientific advancements. What does it mean for our understanding of reality if duality is not merely a quirk of quantum mechanics, but a fundamental aspect of existence? This question invites us to re-examine our perceptions and beliefs, challenging us to embrace the complexity of the universe. The journey into the future of quantum mechanics is not merely a scientific endeavor. It is a quest that intertwines with the very fabric of human curiosity. Each challenge we face beckons us to explore deeper, to question further, and to imagine possibilities that may lie just beyond our current understanding. As we stand at this precipice, we are reminded that the pursuit of knowledge is an ongoing journey, one that will continue to inspire generations to come. What new horizons await us as we venture into this uncharted territory? The answers may yet reveal themselves, illuminating the mysteries that have captivated our imaginations for centuries. The intricacies of quantum mechanics challenge not only our understanding of the universe, but also the methodologies we employ in scientific research. As we look toward the future, we are confronted with current challenges that require innovative solutions. One significant hurdle is the scalability of quantum systems. Imagine a landscape where tiny quantum bits, or qubits, reside in delicate states, each representing a vast array of possibilities. How can we maintain these fragile states long enough to perform meaningful computations? The answer lies in the development of error-correcting codes and robust materials that can withstand the chaotic environment of quantum interactions. Researchers are diligently working to create qubits that are less susceptible to decoherence, the process by which quantum information is lost to the surrounding environment. As we traverse this terrain, we encounter another crucial challenge: the integration of quantum mechanics with classical physics. The theories governing the macroscopic world, such as relativity, often seem at odds with the principles of quantum mechanics. This dissonance raises profound questions. How can gravity coexist with quantum mechanics? How do we reconcile the vast scales of the cosmos with the minuscule realm of particles? These inquiries point us toward the pursuit of a unified theory of physics, a grand framework that harmonizes the laws governing the very small with those governing the very large. This quest for unity has inspired many great minds throughout history. Consider the ambitious vision of physicist Michio Kaku, who has suggested that the formulation of a theory of everything may one day allow us to write the ultimate equation. Such an equation would encapsulate the fundamental forces and interactions of the universe in one elegant expression, shedding light on the interconnectedness of all things. The potential breakthroughs awaiting discovery in this area are staggering, perhaps offering insights into dark matter and dark energy, the mysterious components that make up the majority of our universe yet remain elusive to our understanding. As we delve deeper, we become aware of the role that duality plays in this exploration. Imagine a world where particles can behave both as waves and as discrete entities. What if this duality is not simply a byproduct of our observations, but a fundamental characteristic of reality itself? This profound insight could revolutionize our understanding of the universe. The implications extend beyond theoretical physics. They seep into the realms of philosophy and metaphysics, prompting us to rethink the nature of existence. New technologies are paving the way for advancements in quantum studies, serving as both instruments of exploration and keys to unlocking new realms of understanding. Picture the emergence of quantum sensors, devices that exploit the principles of quantum mechanics to achieve unprecedented sensitivity and precision. These sensors have the potential to revolutionize fields such as medicine, where they could detect diseases at stages previously thought impossible, offering hope for early intervention and improved patient outcomes. Consider the remarkable advancements in imaging technologies that utilize quantum phenomena. Quantum imaging, for instance, leverages the wave-particle duality of light to produce images of extraordinary clarity and detail. This technique could redefine our approach to diagnostics, enabling us to peer deeper into the microcosm of life and uncover secrets that were once shrouded in mystery. Moreover, the rise of quantum communication systems promises to elevate our methods of secure data transmission. Envision a world where the principles of quantum entanglement facilitate instantaneous communication across vast distances, ensuring that our exchanges are not only faster, but also impervious to eavesdropping. This technology could lay the groundwork for a new era of cybersecurity, where the vulnerabilities currently exploited in classical systems are rendered obsolete. As we reflect on these advancements, we are reminded of the interconnected nature of scientific progress. Each breakthrough feeds into the larger narrative of human inquiry, propelling us forward in our quest for knowledge. The interplay between theory and experiment is crucial. As physicists develop new hypotheses, they simultaneously create the experimental frameworks needed to test them. This dynamic relationship fosters an environment ripe for discovery, where each success builds upon the last. Yet the journey is not without its philosophical implications. The more we uncover about the quantum realm, the more we must confront the nature of reality itself. What does it mean for our understanding of consciousness if the universe operates on principles that challenge our fundamental perceptions? How does this impact our sense of self and our place within the cosmos? As physicist Niels Bohr once remarked, we must be clear that when it comes to atoms, language can be used only as in poetry. This poetic language invites us to embrace the ambiguity and complexity of existence, acknowledging that our attempts to articulate these concepts may always fall short. In the face of uncertainty, we find ourselves drawn to the beauty of exploration. The future of quantum mechanics holds the promise of new discoveries that could reshape our understanding not just of physics, but of the universe itself. Each question we pose leads to new avenues of inquiry, compelling us to confront the very nature of reality. As we stand on the precipice of these possibilities, we are reminded that the essence of scientific exploration lies in the journey itself, a continuous unfolding of knowledge that inspires awe and wonder. What uncharted territories await us as we venture forth into the quantum realm? Each experiment, each theory, brings us closer to illuminating the shadows that have long obscured our understanding. In this quest, we are not merely passive observers, but active participants in the creation of our reality, shaping the future of knowledge and discovery for generations to come. The pursuit of advancements in quantum mechanics carries with it not only the promise of new technologies, but also the potential to reshape our understanding of fundamental concepts. As researchers grapple with the complexities of duality, they find themselves at the intersection of physics and philosophy. Imagine the profound implications of a world where the distinctions between particles and waves blur, challenging our traditional notions of existence. This evolving perspective invites us to reconsider the very nature of reality and how we relate to it. The challenges that lie ahead are not merely technical, but also deeply conceptual. How do we reconcile the peculiarities of quantum behavior with the classical world we inhabit? This question resonates in the ongoing dialogue within the scientific community, echoing the sentiments of thinkers who have long pondered the implications of quantum mechanics. As physicists strive for a unified theory that integrates quantum mechanics with classical physics, they explore innovative approaches that may one day bridge these seemingly disparate realms. In this quest, breakthroughs in understanding duality could serve as a guiding light. Imagine a future where quantum phenomena can be harnessed, to create technologies that not only enhance our capabilities, but also deepen our understanding of the universe. The potential for applications spans industries, from telecommunications to energy solutions, as we begin to tap into the enigmatic power of quantum mechanics. As we forge ahead, new technologies will undoubtedly play a crucial role in advancing quantum studies. Picture the realm of quantum simulation, where researchers utilize quantum systems to model complex physical phenomena that are otherwise beyond our grasp. This approach opens up exciting possibilities for addressing intricate problems in materials, science, biology, and even climate modeling. By simulating quantum interactions, scientists can gain insights that were once mere hypotheses, leading to discoveries that could profoundly impact our daily lives. The interplay between theory and experiment remains vital in this journey. As quantum theories evolve, so too must our experimental techniques. Imagine a future where quantum sensors, refined to detect minute changes in physical systems, enable us to observe the universe with unprecedented sensitivity. The exploration of these technologies not only enhances our scientific toolkit, but also brings us closer to understanding the intricate dance of particles and waves that governs the cosmos. In contemplating the future of quantum mechanics, we are reminded that our exploration is a reflection of the human spirit's unyielding quest for knowledge. Each challenge we face serves as an invitation to delve deeper, to ask questions that may lead us toward profound revelations. As we navigate this uncharted territory, we find solace in the idea that the journey itself is as significant as the destination. What new paradigms await us as we continue to unravel the mysteries of quantum mechanics? The potential is vast, and the answers, though elusive, promise to reshape our understanding of existence. As we stand on the threshold of these discoveries, we embrace the complexity of the universe, ready to engage with the profound questions that lie ahead. The future is not merely a continuation of the past. It is a canvas upon which we will paint new understandings, guided by the light of inquiry and imagination.